Hey guys, we have an N54 high pressure fuel pump here. Bought it off eBay, about $80 as a parts pump. Actually, I think it's this side, the high pressure side. If you can see that, has a damaged thread. Thread itself and the port where the metal seal occurs as well. So we're going to tear this down and use it for parts. And then we're going to rebuild another pump with some of these parts, possibly. It's a revision 4 high pressure fuel pump. It's -04. I think the latest pumps on ECS are revision 5 pumps from what I've seen on the web. All right, let's get a diaphragm measurement on the reservoir. .27. So not only does it have damaged threads, it's also a failed pump. Normally, diaphragm depths less than 20 are preferred. You might be able to go up to maybe 22 millimeters, but I did have a pump that was on my car that was at 27 millimeters actually, and it was building pressure, but it did have a slow crank associated with that pump. Now, with this diaphragm, why it's supposed to be 20 millimeters is because it has some amount of fluid in here in this reservoir. So it's essentially called the reservoir, and the oil is routed to the hydraulic side. So when you have thermal expansion going on, this diaphragm and spring in there compensate for that thermal expansion, so it doesn't build, an infinite pressure up in the hydraulic housing. Kind of gives the system some give. And also for cold starts as well. If it's really cold out, your fluid will contract, and you could possibly contract so much that if you didn't have the reservoir, it would pull a vacuum across this rotary seal and you'd pull air into the system. So reservoir for both reasons, hot and cold. And from an accumulator perspective, it also provides extra fluid to the system. So at high speeds, high RPMs, the little pistons in this pump start taking more fluid from the reservoir than they can give back. So it's also used for like transient conditions where you have a really high RPM. So I'd expect that when this is rotating really fast, this diaphragm's actually, and hot of course, is actually less than 20 millimeters. And then when you come back to steady state, just a lower RPM, idle, this diaphragm's the depth will decrease again to some nominal value. So let's get this on the vise and get some hydraulic fluid pouring out of this thing. Hopefully. There's also a chance that there could be gas in this. I've opened another pump before, and this hydraulic side literally only had gas in it. 0 hydraulic fluid left. And that was actually a revision 5, believe it or not. Latest revision of this pump. Only had 20,000 miles on it. That was another $80 eBay purchase. Failed after 20,000 miles. A new pump, new generation, new revision, latest. All fuel on this side. And that right there is the reason why I chose to rebuild this pump, or these pumps in general. Because if it's going to fail in another 20,000 miles, then I'd rather rebuild it myself instead of spending another $1,000 or less on a subpar rebuild. Okay, ready to take the hydraulic side off. And check the torque as I back out one of the screws. So we'll check 20 inch-pounds. This will help us when we retighten the housing. Okay, 20 inch-pounds. Didn't do it for us. Actually, I was at 10 inch-pounds. Now I'm at 20. Okay, still nothing at 20. Let's go 30. Nothing at 30. Let's go to 40. That's what did it. 40 inch-pounds. Okay, now that I broke all the bolts loose, I'm going to try to catch all the hydraulic fluid in a container. From another pump, I actually drained it and sent some of the fluid to Blackstone Labs to have it tested. Check what viscosity it is. I think it's an AW ISO hydraulic fluid. The AW stands for anti-wear. There's different viscosity grades, 32, 46, and 68, I believe. And there we go, starting to pour out. Try to unbolt the rest of this here. So I know others are using like Pentosan, CHF, was it 11S or something, which is a power steering fluid for the BMW. Ooh, making a mess here. But I believe that the power steering fluid is actually too thin after doing a little digging online on general piston pumps. So let's see what Blackstone says. And then I'll update you guys when I have that information. Okay, we good here? Unthreaded? All right. Here we go. Let these bolts drop out. And here's where all the business happens. Got our pistons. I think these are called piston collars up here. Got some springs, some return springs. So they kind of get stuck to the swash plate. That one I had to pop it off. So put them all over here. Okay. So these are going to be our bellows guides or piston guides here that we're going to take off with a homemade tool that I've seen from another video. Had to make my own for it. But we also do want to check these pistons for any wear. Looks pretty good because it will affect the sealing of the pump, the sealing of the pistons, so sealing of the hydraulic fluid in this chamber and its ability to pressurize the fuel, which is sealed by the bellows. So yeah, it looks pretty good. I mean, some, I'd say, typical wear marks. Pretty happy that there was hydraulic fluid in this pump. If there's fuel in the pump, then you got to be a little more worried about wear. Okay, swash plate looks pretty good. It's about typical, so that's great. Okay, actually first we'll start by taking the swash plate off. Let's see, by the way, just for reference, there's a magnetic plug here. Not really sure what that does, but it is right across from the roller bearings, which we'll see. So let me get this tightened up here on the drive piece itself. That's where you want to get it. So you want to get right in the slot here with your flathead. You really want to try to not scratch this polished surface up, because that's where the piston collars ride. They go around here, and this angled swash plate is what is actually responsible for the intake or the displacement of the pistons. So it pushes the piston down, it expels hydraulic fluid into the bellows chamber that we'll look at soon, and then on its retraction stroke, its intake stroke, it's actually pulling fluid out of the chamber, the fluid that it had just pushed in there, so then it can force the fuel side of the bellows to actually suck in fuel into the chamber, the fuel chamber. And this hole here, that's a bleed hole, and it also provides access for the hydraulic fluid to the rotary seal to lubricate the seal as well. But the rotary seal is the #1 cause of failure of these pumps. I'm not fully catching that for you guys either. Okay, let me get a better angle on the vise. Better hold. There we go. To break loose, it just spins right off. Almost there. Okay, and we're off. Let's get our drive out of the vise. And let's move this out of the way for now. Okay, we can take a look at the hydraulic housing. Here's our rotary seal that fails inevitably. So it looks something like that. It's actually properly installed, but you can see the oil that's pooling up here. That is hydraulic oil from the pump itself. So we'll push that out. Comes out pretty simply, just like that. You can see polished surface here as well. And let's look at the wear marks from the seal on the swash plate. Look at that. Some deposited rubber from the seal, whatever material it is, or something like that. Maybe a little burnt hydraulic fluid. But these spin so fast. This is a hardened shaft here, hardened plate as well. These spin so fast that just plain, some type of rubber, maybe BMW N, is causing these wear marks in here, like burn marks almost. So it is going to affect your seal if you reuse this. But this is a 6mm thick seal in here, so the thickness this way. What's on the market like on McMaster and on Amazon, are 7 millimeters thick. So, you know, it actually should pick up on a different location, hopefully, slightly. I mean, these are pretty large wear bands, but hopefully it'll start a little lower than it. So it'll get that polished surface, not the secondary polished surface that the current seal created on there. So then we'll use a 15 millimeter socket to bang this out. Just gotta be careful. Usually don't have this much trouble with it. Yeah, it's starting to go. There you go. Okay. So here's the OD, where the OD seal is made. Here's the ID. There's a wiper lip to keep dust and debris out. And here's your sealing lip with the garter spring, I believe it's called, which helps keep tension on the swash plate for the seal, and clearly a lot of tension if it's creating those burn marks, wear marks. We've got a thrust bearing in here, and then here's our roller bearing. So 2 bearing load surfaces on the swash plate up here, and on the OD right here. You can see that nice angle. So this is made in 2 parts. You have this main angled swash plate piece, and then it's actually press fit, interference fit into this radial band. You can actually see some press fit marks that are meant to bite into this swash plate outer surface here, so that they never come apart. Okay, this looks pretty good overall. There's no other seals in this hydraulic housing. What I do have on another pump, so I have this other housing that I got machined, got a groove machined in there for this retaining ring to help prevent the seal from popping out. I actually saw on one of the pumps that I hadn't rebuilt yet, but I was taking apart, the pump that I had on the car, actually, the seal was popping out, starting to pop out, and that's, you know, from the factory. There was 130,000 miles, I believe, on that pump, though. I'm surprised it lasted so long, honestly. I've seen reports where people are saying that the seal has popped out. That was a cause of their failure from the rebuild that they did. So I did see that someone posted they used a retaining ring, so I figured I'd use that feature as well to prevent mine from popping out. I do need to, I bought a tool actually from McMaster. It's an internal groove cutting tool sized for this snap ring. So the machinist will take off this O-ring. Oh, see, there's that magnet again, catching screws. They're gonna hold with a collet or a 3-jaw chuck, likely a collet for better run out, on this face. And I had him put a little tape on this thrust bearing to keep it in place, so while this lathe is spinning the part, the thrust bearing is not all over the place. But basically, you come in with this tool, and I had him come in right where this at the center point of this groove tool is where I had him machine into the center point of the end of this chamfer here, just to keep it as far enough away as possible from this swash plate face. Like I said, the seal, aftermarket seals, they are thicker than this OE seal. So the last thing I want to do is, by putting a retaining ring in, causing the seal to go further down, and also the seal being thicker itself. Last thing I want to do is have it abrading against this surface, causing more problems. So I try to bias the retaining ring as high up as possible while still having enough material on this outer face, retaining ring face. So top side of the groove, retaining ring groove, so that it won't get pushed out. I also don't want the retaining ring to get pushed out and get caught up with this drive either. Okay, so now that we got that all squared away, and I made a huge mess, more of a mess than I wanted to make right now, we will go for this guy here. We'll pop these piston guides out. But first, I'm actually going to remove the solenoid. Let's tackle that first, because I don't want it to interfere with the grip I'm going to get on my vise, my bench vise there. So I'm going to plug this just with my finger. I'd like to do that. I don't think that's gonna work actually. I just don't want any more fluid to come out. I guess I will be dumping it out anyways, so I can replace it with new fluid, so I'll just flip it over, it's fine. All right, now, what do we got here? I think we got a 4 millimeter bolt to take that out. So, I believe this actually, let me get a torque wrench. Let's do the same thing that we did on the hydraulic housing bolts. Check the torque on these. All right, that's also 40 inch-pounds for these solenoid bolts. Just about. A little over wouldn't kill you. You know, if it was 30 inch-pounds and we went 40 on the retighten, it's not really a big deal. Such a small difference in torque. Okay, put those bolts there. So this is actually usually hard to take out. Barely made progress. There you go. All right, now we have 3 seals here. We have the high pressure side seal. That's why there's a backup ring on this side. So this actually is a separate piece of material here, if you can see that. That's called a backup ring. It's used on high pressure O-ring seals above 1500 psi, which this is. Operating pressure is what on the high pressure? 2200 psi nominal. Can go up to 3000, I believe, in certain cases. So high pressure seal here. This is actually, it's like a solenoid. It's really a pressure regulator. So basically controls the flow from the low pressure side through to the inlet or check valves of the fuel chambers. So a flow control valve. I think I called it a regulator just now. More so a flow control valve. So if it needs more flow, it opens this valve up more or less. It's a little like pop it in there with a spring. So it opens that up more or less as it needs to bring more flow in from the low pressure side. And again, this seal is connected to the high pressure side, but there's a seal there, so you're not bringing in the high pressure fluid into your low pressure side. There is also a screen filter here, by the way, a very small screen filter. I'm not sure why that's the case. I'm sure some flow might go through from the high pressure side. I'm not sure why they're doing that and how much pressure is really coming through, but maybe it's possibly to balance the piston against a magnetic force here. I'm not sure, complete guessing at that point. But these are all O-rings we'll be replacing with Viton as well. That's something I haven't mentioned yet. We're going to be replacing all the O-rings on this part, internal part, with Viton, anything that contacts gas. Because I do run ethanol blends in my car, so when I did remove the pump from my car and take these out, they literally they were swelled up, so they actually took up the whole gap space here, the whole width of the O-ring groove, and they also tore apart super easily. So they weakened, they swelled up, and they tore off. I didn't even have to use a pick to take them off. Literally just tore them off because they're BUNA N O-rings, which is not fully compatible with ethanol, but Viton is. So that's why we're going all Viton on the fuel side. See how much fluid we dumped out. Oh, not bad from the reservoir. Thought I'd dump out more than that. That's good. Okay. All right, let's retighten this in the fixture. Now that I took the solenoid off, it'll fit better in my fixture. Okay, feels pretty tight. All right, now that I have my tool, you can see it's just a long rectangular bar, steel bar with 2 holes in it for number 20 drill bits. Let's see. I got carbide drill bits, number 20. Here we go. Come on, get focus. Number 20, carbide, 118-degree point. Drill bit, the point isn't important for this. I'm just using it as a hardened dowel, essentially. To grab into these holes, 2 of these holes here, and allow me to remove the piston guides. Okay, so I usually start with 1 in the hole, and then I look above. There you go. I think that's the next one. Somewhere in there. Yep, there we go. Now it takes a good amount of force to take these off, to break these loose. So look how far back I am here. This is probably what? 2.5 feet or so of leverage that I have here. All right, let's pop the first one off. There you go. My workbench was actually moving before I even got that to break loose. a pretty good amount of force. So when I put it back on, I'm gonna have to tighten it just as hard. So then I can use some needle nose pliers to finish taking this off. Finish unthreading this, I should say. I'll take the other ones out, remove the other ones off camera, but I'll get to this one so I can explain a little bit what's going on in here. Oh. Got a little wear going on in there. Look at that. Interesting. Okay. But anyways, this is the piston guide and sort of, you know, bellows guide as well, because there's a pin on the inside at the end of the bellows that fits through the center hole. But the other four, like circular, semicircular looking ports are actually the flow ports for the hydraulic fluid. So it meters the fluid coming out, you know, being retracted with the piston, and also the fluid being pushed in, displaced into the bellows as well. And there's also a sealing face here. See if you can see it. Kind of hard to see, but yeah, you can see a little wear there. So that's actually creating a metal seal up on the bellows. So I will show you another bellows. So there's a face up here. See that stepped face? The top of that face is a hydraulic seal. So it prevents the hydraulic fluid as it's being pushed by the piston throughout these flow ports into the bellows. It's preventing that fluid from backdrafting up and up these threads. But there is also an O-ring on the OD of these bellows. So I can see the bellows here, the groove there. Because essentially there's that metal seal to stop the hydraulic fluid from coming out into the threads this way, but there's nothing stopping the fluid from the hydraulic side leaking past the threads and through to the fuel side. So that's actually what that O-ring is doing there. As we'll see when I pull out this other bellows here, there's also another metal sealing surface. I'll give you a close-up in the bore in a sec. But there's also another metal sealing surface for the fuel side. So normally when you talk high pressures, unless you're using a backing ring, you don't really want to use O-rings. You want metal seals, and that's what the manufacturer did here, the designer. So again, this O-ring really is, unless you have of course a failure here at this seal, which is possible. You know, this is kind of like a secondary, I'll say seal, backup seal, but it also does passively prevent this fluid from the hydraulic side leaking past the threads and down into your fuel side. Okay, now to take out this bellows. So like I was telling you, there's a metal seal here. This metal sealing face is actually cold welded to the housing, to the steel housing. So I've seen a trick online on YouTube, another video where someone's using paint can openers, and it actually did that slightly, and it did, you know, ruin, or I'll just say dented the bellows a little bit. So I actually realized I was denting it. I stopped, and then from another video I saw someone just hammering on the bellows pretty pretty firmly. Let's check if it moved. To break that cold weld at that metal seal. There you go, pop. That's it. It's off that easy. And it's not damaging the bellows when you do this. You know, if once it popped out, you know, you went back and repeatedly hammered it, yeah, you could damage it possibly, but that didn't just damage it there because, again, it's sitting on this metal face here. Let's see if I can get a close-up. Right on this face, right there. That's where it's sealing. You can actually see a wear mark here, I believe. If you can see that sealing face there's like a ring. So again, you're just breaking, you know, the cold weld, I'll call it, from that high amount of torque where the materials galled into each other. You're just breaking that loose, and then this bellows just pops up, just like that. So then we can remove this O-ring, replace it with a Viton, and reinstall, and do the rest of the other two. And there's also a spring in there, might as well point out. So this is another return spring on the fuel side. So we have a fuel side return spring, and we also had the hydraulic side return spring as well. Both pretty stiff. I'm not going to push on it too hard. This one's definitely stiffer than this smaller diameter spring that's in the piston.